So today we're going to look at covalent bonding, and the first thing we're going to do is we're going to define what we mean by a covalent bond, right? So what exactly is a covalent bond? A covalent bond is defined as the following. It refers to the electrostatic force of attraction between between positively charged nuclei between the positively charged nuclei of both atoms and their shared pairs of electrons. Shared pairs of electrons. Could be a pair of electrons, it could be pairs of electrons. Right? So here's a diagram that illustrates a covalent bond, right? So let's say we have two atoms. We have two atoms that are overlapping. And these are their shared electrons, right? And the reason why these two atoms are held together is because these shared electrons are attracting the nuclei of both atoms towards the shared pair of electrons, right? So the shared pair of electrons is what the electrostatic force of attraction between these shared pairs of electrons, right, and the nuclei is what keeps these two atoms together. Okay, so that's what we mean by covalent bond. Okay, the next thing we're going to look at are dot and cross diagrams. Right, this is something that you guys have already seen. Right? We're going to look at dot and cross diagrams, and we're also going to look at what we mean by the Lewis structure. What do we mean by the Lewis structure? Okay, so what's a dot and cross diagram and what's a Lewis structure? So we're going to look at different molecules here. Okay, so let's start with an example, right? Let's say that I have carbon dioxide, right? So in carbon dioxide, we know that carbon has 4 valence electrons, so it wants to make 4 bonds, whereas oxygen has 6 valence electrons, it wants to make 2 additional bonds, right? That's what we learned previously about the octet rule, right? So what we can say here is that if you look at the dot and cross diagram for carbon dioxide, it looks like this, right? What we have is we have we have a double bond between carbon and oxygen here, and we have a double bond, right, between carbon and oxygen over here, right? Now let's say that I'm gonna include a key. Okay, and we should make a habit of including a key here. Let's say the dot represents atoms of oxygen and the cross represents electrons of carbon. Okay, so the dot represents oxygen, electrons from oxygen, and the cross represents electrons from carbon, right? Now we know that carbon had 4 valence electrons, right? They're all bonded here, right, in these two double bonds, and oxygen has 6 valence electrons, right? So if you look at this oxygen atom, two of the 6 valence electrons are in the bond, and it has another two pairs of electrons, right? There's another 4 electrons, so we're going to show them like this, right? Similarly, the other oxygen atom also has 4 unbonded electrons here. Right? It also has 4 unbonded electrons, and these pairs of electrons are called lone pairs. These pairs of electrons are called lone pairs, right? These are pairs of electrons that are unbonded. Okay? Pairs of electrons that are unbonded. Now you can draw the dot and cross diagram like this as well if you like. Okay, you can draw it using the circles. I don't like drawing it this way because it just takes a lot more space, right? But you can draw it like this as well. All right, we have carbon and oxygen, and then we have the 2 lone pairs and oxygen here, and you have the double bond here, and then you have the 2 lone pairs and this oxygen atom here. Okay, so you can draw it this way, but I'll be sticking, in most cases I'll be sticking to drawing the dot and cross diagrams this way, right, rather than drawing the circles. Now, what does the Lewis structure of carbon dioxide look like? The Lewis structure of carbon dioxide is the following. Okay, it shows clearly that there are double bonds between the carbon and the oxygen, but it also shows the lone pairs of electrons in the valence shell. So we have 2 lone pairs of electrons on this oxygen atom, and we have 2 lone pairs of electrons on this oxygen atom, right? So this is the Lewis structure of carbon dioxide, whereas this is the dot and cross diagram for carbon dioxide. Okay. In the Lewis structure, we only use dots to represent electrons, right? There's no cross. Okay. So you use lines to represent bonds, right? Each of these lines represents 2 electrons. So if you have 4 shared electrons, that's a double bond, right? You have 2 bonds here, you have a double bond here, right? That's 4 shared electrons. Each line represents 2 electrons, bonded, 2 bonded electrons, whereas here these dots represent the unbonded electrons. So again, this oxygen has 2 lone pairs, and this oxygen also has 2 lone pairs. The next example that we're going to look at is ammonia. Nitrogen is in group 15. So according to the octet rule, nitrogen wants to form 3 bonds, right? It wants to gain 3 electrons to complete its octet, right? So over here, right, what we have is nitrogen forms a single bond with this hydrogen, it forms a single bond with this hydrogen, and it forms a single bond with this hydrogen, right? And obviously hydrogen just has 1 valence electron. Hydrogen just has 1 valence electron, right? Whereas which is bonded for each of the hydrogen atoms. Nitrogen has 5, 3 of them are bonded, and then 1 of them will be unbonded, right? So ammonia also has, the nitrogen has a lone pair of electrons, right? Here again the key is that I'm using a dot to represent nitrogen, electrons from nitrogen, and a cross to represent the electrons from hydrogen. In the Lewis structure, we have 3 single bonds between nitrogen and hydrogen atoms, right? And we have a lone pair of electrons. So this is the Lewis structure for ammonia. Let's say that we have the example of ethene next, right? Ethene is C2H4, right? That's the molecular formula. It's a molecular formula for ethene. So if you look at ethene, we know that ethene has carbon-carbon double bond, and the bonds between the carbon and hydrogen are single bonds, right? So we have a carbon-carbon double bond, and then we have single bonds between the carbon and the hydrogen atoms, right? So if you look at the dot and cross diagram for this, right, we have 2 different carbon atoms, right? So just to highlight this, what we'll do is we'll use one of the dots for one type of carbon atom, right, and the other type of dot for the other type of carbon atom. Okay, so this is for, right, so they're both representing electrons from carbon, and then the X represents the electron from the hydrogen. So over here, if you look at the dot and cross diagram, we have a double bond between the 2 carbon atoms, right? We have a double bond between 2 carbon atoms, and then we have a single bond between the carbon and hydrogen here, and we have a single bond between the carbon and hydrogen here. Similarly, we have a single bond between a carbon and hydrogen here, and we have a single bond between a carbon and hydrogen over here, right? So here again, 2 pairs of electrons being shared, that's a double bond, right? Every pair of shared electrons is a single bond. So if we have 2 sets of paired electrons, right? Two pairs of shared electrons, that's a double bond, and then we have, right, these single bonds here. Now the next thing we're going to look at are exceptions to the octet rule. Exceptions to the octet rule. One example that we have of an exception to the octet rule is boron trifluoride, okay, BF3. So boron is in group 13, okay, boron is in group 13, and it has 3 valence electrons, okay, it has 3 valence electrons, right? So what we have is boron has 3 valence electrons, right? And it's going to make a single bond, with each of the fluorine atoms, right? Now fluorine has 7 valence electrons, right? Fluorine has 7 valence electrons, right? And if you look at the dot and cross diagram, this is the dot and cross diagram for BF3, right? Clearly show all the valence electrons, right? And what we see here is that when we look at fluorine, each of the fluorine atoms has a complete octet, right? Each of the fluorine atoms has a complete octet, right? Fluorine had 7 valence electrons, and now because of the extra electron from boron, this fluorine has an octet, this fluorine atom has an octet, and this fluorine atom has an octet. But if you look at boron, on the other hand, right, it had 3 electrons, and now it's sharing 3 additional electrons, so it has a total of 6 electrons in its valence shell, which is lesser than the octet. So this is an example of a stable molecule that doesn't obey the octet rule. If you look at the Lewis structure for this, right, you have BF3 like this, right? So this is the Lewis structure, and again we can clearly see that we have a complete octet for each of the fluorine atoms, right? We have 2, 4, 6, and then 8, right? 2, 4, 6, 8, and then 2, 4, 6, 8. So fluorine has a complete octet after making that single bond, but boron doesn't have a complete octet, right? It has 6 valence electrons even after the bonding has taken place. Okay. So this is an example of a molecule that doesn't obey the octet rule. So here we have the Lewis structure, right? This is the Lewis structure. Another example that we have is BeCl2. Beryllium chloride. Beryllium is in group 2, right? It has 2 valence electrons. Right? It has 2 valence electrons. And it's making a single bond with each of the fluorine atoms, right? It has 2 valence electrons. It's making a single bond with each of the fluorine atoms, right? And here we have the dot and cross diagram for beryllium chloride, right? Showing the valence electrons. So the Lewis structure for beryllium chloride simply looks like this, right? We have beryllium making 2 single bonds with each of the fluorine atoms, and then we have these 3 pairs of electrons. Okay. So this is the Lewis structure for beryllium chloride, and this is the dot and cross diagram. Again, we see that beryllium is not completing its octet, right? It just has 4 electrons here in its valence shell, right? So it's not, so here boron has an incomplete octet, here beryllium has an incomplete octet. So these are examples of compounds where the atoms, right, have fewer than 8 electrons, right? They don't complete their octet. Now we also have examples. Of compounds where we're going to exceed the octet rule. We're going to exceed the octet rule. So exceeding the octet rule. Okay. When we talk about exceeding the octet rule, it applies to compounds. Right? It applies to period 3 elements. Right, and onwards. Okay. So it doesn't apply to period 2, right? It doesn't apply to period 2 because the second shell can only hold 8 electrons, right? So the maximum you can have is an octet for a period 2 element, but a period 3 element, the valence shell can hold up to 18 electrons, right? So again, this is because the third shell can hold up to 18 electrons. So period 3 elements can exceed the octet. One example that we have is sulfur hexafluoride. Okay. Sulfur hexafluoride. Sulfur hexafluoride has the molecular formula SF6. Okay. SF6. So here, if you looked at the dot and cross diagram, right, we have the sulfur atom. That's bonded to 6 fluorine atoms, right? It's bonded to 6 fluorine atoms. Okay. So this is the dot and cross diagram for sulfur hexafluoride. Right, it's bonded to 6 fluorine atoms here. We have F, 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 right? Now sulfur has 6 valence electrons. It's in group 16. So it has 6 valence electrons. And fluorine is in group 17, right? So fluorine can't exceed the octet, so it can only make a single bond. Fluorine cannot exceed the octet because it's in period 2, right? So if it has 7 valence electrons, it can only make a single bond. And it now has 8 valence electrons, right? So what's happening here is that each of the fluorine atoms is making a single bond with the central sulfur atom, right? And sulfur can make 6 single bonds because it has 6 valence electrons, right? It has 6 valence electrons. So sulfur is making a single bond with each of the fluorine atoms, and then obviously if you wanted to complete the dot and cross diagram, you have to show all the valence electrons for fluorine as well. Okay. So This is the dot and cross diagram for sulfur hexafluoride, right? Now, if we notice, the sulfur atom is exceeding the octet here. The sulfur atom is exceeding the octet. It had 6 valence electrons. Okay, the cross here represents the electrons from sulfur, and the dot is for fluorine. Right, sulfur had 6 valence electrons, and when it ended up making a single bond with each of the fluorine atoms after bonding, right, the sulfur atom has 12 electrons, right? So sulfur now has 12 electrons. So it has 12 electrons, so it's exceeding the octet, right? It's exceeding the octet. Again, in dot and cross diagram, we're showing the valence electrons, okay? And for sulfur, we had 6 valence electrons, but once sulfur makes a single bond with each of these fluorine atoms, right, the sulfur now has 12 electrons, so it's exceeding the octet. Fluorine, on the other hand, cannot exceed the octet because it's a period 2 element. Okay, the valence shell can only hold a maximum of 8 electrons, right? The next example that we have of the octet being exceeded is phosphorus pentachloride. Phosphorus pentachloride. Now, phosphorus pentachloride is the formula PCl5, right? And if you look at PCl5, what we have is we have a phosphorus atom, right? Phosphorus is in group 15, so it has 5 valence electrons. It has 5 valence electrons, right? So again, it's making a single bond with each of the chlorine atoms. Okay, it's making a single bond with each of the chlorine atoms. Okay, so again, phosphorus has 5 valence electrons, right? It has 5 valence electrons, and it's making a single bond with each of the chlorine atoms, right? And remember, chlorine had a total of 7 valence electrons, right? One of them is shown in the bonds here, and then you have 7, right? There's 6 more. Right, so you just have to. So this is the dot and cross diagram for PCl5. Okay. This is the dot and cross diagram for PCl5. So over here again, phosphorus is exceeding the octet, right? We have 10 valence electrons. It had 5, and now it's sharing 1 with each chlorine atom. So now we have a total of 10, right? Each of the P and Cl atoms are sharing 2 electrons in total. So we have 2 times 5, which is 10 electrons, right? The phosphorus has 10 electrons. So it's again exceeding the octet. Another example where you exceed the octet is sulfur dioxide. Okay, in sulfur dioxide, what do you have? In sulfur dioxide, you have sulfur, which has 6 outer electrons, right? And it's actually making a double bond with each of the oxygen atoms. It's making a double bond with each of the oxygen atoms, right? And then sulfur has a total of 6 valence electrons, right? 2 of them are bonded in this double bond, 2 of them are bonded in this double bond, and then you have 2 more, right? And then oxygen obviously also has a total of 6, so you have 2 lone pairs in the oxygen atom, right? Again, sulfur has 6 valence electrons. 4 of them are in the double bonds, and then 2 of them are unpaired, right? You have a lone pair. So here again, sulfur is exceeding the octet, right? You have 4, 4, and then 2, right? So you have 10 electrons, right? Okay, so it's exceeding the octet again. Okay, the Lewis structure looks like this. You have a similar thing with sulfur trioxide. That also exceeds the octet. Sulfur trioxide also exceeds the octet. For sulfur trioxide, you have 3 double bonds with the oxygen atoms, right? So now the central sulfur has 12 electrons. Okay, the central sulfur has 12 electrons, right? Because it had 6 electrons, and each of those 6 electrons is now bonded. So you have 6 bonds here, right? You have 3 double bonds. You have 3 double bonds, so you have 6 times 2, right? 2, 4, 6, 8, 10, 12. So now the central sulfur has a total of 12 electrons, right? So again, it's exceeding the octet, right? And this is the Lewis structure. If you show the lone pairs of oxygen, right? And here, of course, we have the Lewis structure for sulfur dioxide, right? Another example that we have is ClO2, chlorine dioxide. Okay. Now, what do we have with ClO2? In ClO2, what we have is chlorine is making a double bond with each of the oxygen atoms, and chlorine has a total of 7 valence electrons. 4 of the electrons are bonded, right? 2 electrons here and 2 electrons here, and the remaining 3 are unbonded, right? And oxygen has a total of 6. 2 of them are in the bonds, right? And then 4 of them are unbonded. So this is the Lewis structure for chlorine dioxide, and then the dot and cross diagram will look like this. Right? And then you have oxygen, and then you have lone pairs on oxygen, right? And you have the 3 unbonded electrons in chlorine. So here the central chlorine has 11 electrons.